We present TrustMAE, a framework for detecting defects under the presence of noise in the training data. Detecting defects is challenging because they can be anything, and they do not necessarily look alike. It is infeasible to collect a dataset that covers all possible defect types, making it difficult to employ standard classifiers. A common approach is to train an autoencoder on only normal images. At test time, it would have difficulties reconstructing defects since it was only trained on normal images. We can then get the difference between the two and treat large differences as defects that we want to separate out. However, in practice, autoencoders can be overly general and reconstruct defects as well. This is further aggravated if noise or defective images leak into the training dataset. To address these problems, we propose TrustMAE. It consists of 4 key components that work together to achieve resilience to noise in the training data. First, the memory autoencoder reconstructs a normal version of the input. Inside it, we use sparse addressing and trust region updates to avoid noise contamination. Lastly, the spatial perceptual distance computes the difference between the two images, which we can then use to discriminate normal from defective. The memory autoencoder constrains the reconstructions to be within the memory space. It works by approximating the encoded vectors using a convex combinations of vectors stored in the memory. We could think of the memory as learning a set of features or puzzle pieces that we could use to reconstruct the input image. An advantage of incorporating memory is that if we could ensure that the memory space is clean, that is defect-free, then we could ensure that it will not reconstruct defects. This is in contrast to standard autoencoders, which can produce unexpected reconstructions for inputs outside the training data distribution. Problem now becomes, how do we ensure that the memory space is clean? Before going to the solution, let us first look at the memory access patterns. Without any restrictions, the network learns to spread information across all memory slots. After all, using more memory slots give it more degrees of freedom for reconstruction. This is not a problem if the training data is clean. However, if it contains defective images, then the network will also spread defect features to all memory slots, making it harder to separate them. We incorporate sparsity in the memory addressing to make the information more concentrated to a select few memory slots. This makes it easier to prevent unwanted features from contaminating the memory slots. It also prevents the model from using a complex combination of vectors to reconstruct defects. We implement this by choosing the top k closest memory slots for reconstruction, combined with the margin loss to prevent the network from storing redundant features. Now that we have sparse addressing, how do we prevent defect features from contaminating the memory? This is where our trust region memory updates come in. The idea is to pull vectors within the trust region closer to the memory slots, but push away everything outside it. There are 2 key assumptions for this to work. First, defects should not always appear in the same location. This significantly reduces the proportion of defects on the patch level. Second, normal data should have regularity in appearance, making it easier to reconstruct normal in the early stages of training. This means that normal samples are initially mapped closer to the memory slots than defective samples. We implement the trust region using this loss function, where this term is the distance to the closest memory slot. Delta 1 defines the trust region boundary. We consider everything below the average distance as normal and everything above as potentially defective. Delta 2 is a threshold to prevent the model from pushing the distance to infinity. After reconstructing a normal image, we need to compute the distance to normal. We observe that shallow distance functions such as MSE and SSIM are too sensitive to the slight shifts and inaccuracies in the reconstruction. This is problematic when we are after texture similarity rather than exact reconstructions. We instead use differences of deep features to compute the distance, allowing us to capture texture and other high-level features. It also contains invariances learned by the network and making it more suitable for texture similarity. We could observe that our spatial perceptual distance assigns large differences on defective regions while assigning low differences on normal regions. Our approach outperforms several state-of-the-art baselines in the noise-free setting on both defect classification and segmentation. In the noisy setting, we could observe that our method maintains a competitive performance across various levels of noise and outperforms the standard memory autoencoder that our model is built on top of. We could also observe that our model prevents defects from being reconstructed, despite having over 30% of noise in the training data. Thank you for listening.